one cycle of repetitive motion. So the period of the second hand on the clock, 60 seconds. Period of the minute hand, 60 minutes. Period of the hour hand, this is on the clock, but 12 hours in most cases. All right, let's start out with our favorite force diagram. All right, I got M1, I got a string, and I got M2. Got a new color here, so lay it on me. What are the forces?
No force. Does it stay on the floor or is it?
M1 is suspended in the air. M1 is not on the floor.
Okay, the tension.
The tension.
Up.
All right, so FT1 or just FT. And FT. Assume it's an ideal room.
Oh, wait for it to down. And also a normal force into the table.
Yep. All right, so which way is it on M2? Yep, so I got a normal force going this way.
And
And,
tension.
all right, I got a tension pulling to the left, here to the right. It's an ideal rope, so those tensions should be the same. That's why, if you want to put a subscript, those would have the same subscript, those would, as I think a number of you know. And there's one other force involved. That's not going to impact the problem, but there is one other force involving acting on one of these three objects. Obviously, we left the ground and the table out of it. But what's the one other force acting on one of these objects?
Any resistance?
Say it again.
Any resistance?
Sorry, I did not understand.
That's probably what it is.
Friction?
Any resistance.
Oh, air resistance. Ignore air resistance. Yes, in reality, right. This is sort of an indication that we're not worried about too much about reality right there.
Friction?
No, it's frictionless, so we don't have to worry about that.
Is there something causing it to go around in the circle?
We assume it's already started,
Okay.
it's already moving in the circle.
Okay.
With physics, we often don't care about how it got there, we just care about it's there, let's deal with it now. Why is the rope bent?
Oh, because there's something holding it there, so there's a normal force, probably presumably between the table and the rope.
Yeah. So, and that normal force, I mean, all this stuff is going to be rotating around as it goes. All right, so what I care about is this and this. I feel like it shouldn't be doing that. Referring to the board, not the problem. All right, here we go. We've got, well, mass 1 is in equilibrium. I said it doesn't want to move at all. So if it's in equilibrium, what does it tell us about those two forces?
Equal to 0.
Say it again.
Equal to 0.
What do I do with them to get them equal to 0? They're each equal to 0?
You add them up and they get 0.
Yeah, the sum is 0. So the force up, which is the tension, and the force down, which is the weight, they are equal to each other, so the tension equals the weight. And the weight, formula for weight, and so that is 5 kilograms. And let's put this on a strange world where G is equal to 10 meters per second squared. So 50 newtons. That's the force down, that's the weight. So I now know the tension. Tension is 50 newtons. All right, so that's mass 1. Mass 2. I got 3 forces acting on it. Is the mass accelerating up or down?
No.
So the normal force and the weight equal each other there. So Y2 is equal to weight 2. I guess I should put weight 1 there. M1. So that would be 3 kilograms times 10 meters per second squared. So my normal force is 30 newtons. We're not going to do anything with that. That was just sort of a side note. What I care about is the unbalanced force, because this thing is accelerating. It's traveling in a circle. Therefore, the direction changes. Therefore, velocity is not constant. Therefore, there's acceleration. I'm going to plug in the Newton's second law. F equals ma. My force is my tension times mass 2 times my acceleration. It is centripetal acceleration. I'm just a little a sub c there. The tension and the acceleration are in the same direction, so I'll just consider that positive direction, or I can consider that the negative radial direction and the minus signs cancel out. My tension here I know is 50 newtons, and that's equal to 3 kilograms times my centripetal acceleration, which is v squared over r. R is a half a meter, so I got 50 newtons is equal to 3 kilograms times v squared over 0.5 meters. So v squared is equal, I need to get this stuff over here. Actually, 3 divided by 0.5. What is 3 divided by 0.5?
6.
That's 3 times 0.5. 3 divided by 0.5
1 point. Wait,
should be 6.
I had it right the first time. We'll have them right.
All right, so this will be 50 divided by 6. And so v, what's the speed?
8.8.3333.
8 point?
3333.
No. Because 8 squared is 64, this is less than 64.
That's 8.3.
Oh, that's this.
Yes.
Okay, and then take the square root.
2.8867.
Meters per second.
Yes.
How'd you get 0.5 again? Oh,
I
0.5.
gave it to you the problem. All right. Other questions at this point? Because we haven't answered the question yet. We found the speed, which is critical to find the period. All right. What's the formula for speed?
Distance over time.
So if we're talking about this thing going around one circle here, what's the distance it travels?
2pr.
So that 2.8867 meters per second is equal to 2 pi r, that's the distance it travels in one cycle, divided by the period. So 2.8867 meters per second is equal to 2 times pi times 0.5 meters divided by the period. And so the period becomes pi divided by 2.8867. That would be meters, that's meters per second. I did 2 times 0.5, which is 1, that's why it's just pi now. And then I moved the t into 2.8867 across the diagonal.
Are we using a number for pi, like 3.5?
Yes, please use a number for pi.
One point zero eight nine.
1.089.
1.088
88. Yeah, same thing?
seconds.
Yes. You got the same? All right, so we now know how long the thing goes around. Some questions before I ask a follow-up question, and then we do one more example, then take a break. If mass 2 were not swinging at all, what would happen?
This one will fall to the ground.
What?
Yeah, if mass 2 were not swinging at all, if it were just still, or if we stopped the turning, what would happen?
Mass one would go down.
Yeah,
Yeah, mass two pulled towards the center.
absolutely. All right, so that gets pulled to the center, that falls. Matter of fact, well, or we'll at least start out on the other problem. Now, instead of swinging it on a table, what we're going to do is we're going to have a tube here that I'll hold on to. Mass 1, mass 2. If this angle is small, so I'm going to label. So the way that you would indicate the angle is small is if the angle is much less than 1. So you've got the 2 less than symbols, that means much less than. Then we can treat it as if mass 2 is perpendicular. That part of the string is perpendicular to that part of the string. If this is a half meter here, this is 5 kilograms and this is 3 kilograms. How long does it take for mass 2 to move all the way around the circle so that mass 1 does not fall or move up? I feel like somebody in here knows the answer already. And just afraid to say it.
Not the same.
So what's the answer?
Is it just the same? Because
Yeah.
there's no new force acting on it.
Yeah, matter of fact, we took 2 away. The big difference between these two is the fact that, oh, it's gone now. this right here goes away. But we didn't use that anyway. Now, this assumption right here that this angle is just small, that it's not going to hang down much, in 151 and 251, we take that angle into account. 110, we don't, but we do the math just slightly differently in the lab form of it. So you end up with the same answer. But on that note, let's take a small break. Let me go grab a bigger tube than the one I have right here. And we'll actually perform it live. There we go. Just need background music. So what we're going to do is we're going to do this experiment and try to predict what the mass of this stopper is. I just took the measurement of it, so I have it written down. No doubt whatever we get as our prediction will be spot on with what I've written down. I've done this too many times. I'll be shocked if we're within 10%. All right, so as this thing spins, now right now the tension of the string is, the tension is the centrifugal force. The tension is being supplied by my hand. I don't want to do that. I want to put weights at the end of it that will keep it from spinning, or keep it from slipping. So what I'm going to do is I'm going to put a 100-gram mass on the end. Now, this is less than 100 grams. If this were frictionless, then it would be sliding like that. It's not frictionless, so that has to be taken into account somehow. There is an assumption that the friction on the end of this is relatively constant, so in the lab form of it, you do several different weights down here, several different measurements for each weight of the time, and then you do a graph to sort of take out common errors. I also need to make sure that the radius here is relatively constant. Now to do that, I have tape down here, and as I swing it, I want the tape basically to stay the same distance. So if it's falling, I'm going too slowly. If I want to move it up, I just swing it faster. And then I want to try to maintain that. I also want this to, too fast. I think I can put more weight on the end just so that it slides better. So I got 150 grams there. Now it slides. All right. So if I don't swing it, it will slide, but I am going to swing it to keep it from sliding. And I want to maintain that distance. So when it's about right there, somewhere around there, I need to know that distance because that's the radius. Someone write this down. The radius is 58 centimeters. And I'm going to need you to time. We're going to time how long it takes for me to swing it around 20 times. I would recommend if you're timing it, I'm going to start swinging it, and then when it's basically between me and you, start the timing, and then count to 20. Silently, so you don't mess up someone else's count, because people might start at different times. I assume we got Jennifer ready to time, Dulce, Ty, Emily, Ellie, Layla. All right, let me get it up. Let me get it going first. right, start timing when you're ready. Anyone still timing? I'm trusting everyone's finished timing. Did you time for 20 rotations? I'm starting to remember if I actually said 20 or not. Okay, I did. All right. The time for 20 rotations.
13.73.
13.73.
13.12.
13.51.
Sensing a pattern here.
15.88.
15.88.
13.8.
14.05.
All right, so we can go with it as is, or we can throw out top and bottom, or top two and bottom, go to medium, average them all. I got a nod for averaging them all, so let's average them all.
I got 14.015.
14.015.
Yep.
Anyone else get the same? Okay, all right. Anyone get something different? All right, seconds. That's the amount of time. That's the time for 20 revolutions. Therefore, how much time is it for one revolution? Or how would you find it?
That number divided by 20.
Yeah. So my period would be this divided by 20.
0.70075.